Welcome to the presentation on aerosols and particulates emitted while speaking and singing. This is an ongoing research project in the Mechanical Engineering Department of the Herf College of Engineering in collaboration with the University of Tennessee Health Science Center. In this presentation, we will introduce the topic of research and take a brief look at some of the literature that exists about the topic. Then we will take a look at our experimental setup and data collection methods, some of the earliest data that we have gotten from the lab, and talk about where we hope this experiment will go in the future. The purpose of this research is to investigate the number of airborne particles expelled by someone who is speaking and singing. The project aims to visualize this data and correlate it to specific vocal activities in a way that has not been done before. The particles we're interested in, aerosols and droplets, range from 1 to about 100 microns in diameter and are not visible to the naked eye in most cases. Aerosols, defined specifically as particles less than 10 microns in diameter, are a subject of interest because virus-carrying aerosols can stay airborne for quite a long time and travel through a space, posing a risk of infection. So why study aerosols? Well, in light of current events, airborne transmission of sickness has become an obstacle for many activities in which face-to-face contact is unavoidable. Examples of these include dentistry, speech pathology, music education and performance, athletics, and others. Since wearing a mask is impractical or impossible for such activities, new safe practices must be implemented based on a better understanding of exposure to exhaled particles. Specific vocal activities will be selected for the research that are relevant to these scenarios in order to inform this process. And as a quick note, is this a mask study? Well, not at first. The research goal initially is to inform safe practices for situations that by definition cannot involve the wearing of masks. Eventually, though, this method could be used to measure the effectiveness of safety measures like masks that are implemented in other scenarios. Previous studies have investigated the number and size of exhaled droplets. Many studies note that these values vary widely between publications on the topic. An article published in 2009 estimated an average size of 50 to 100 microns for collected respiratory droplets, but collection is an intrusive method that excludes aerosol-sized particles. Optical studies of particle counts provide high-quality images and videos of particulate matter and are non-intrusive. But these studies usually focus on more abrupt events like coughing and sneezing, so little data of this kind exists for more regular events like singing or having a conversation. A variety of exhaled airflows have been well documented using Schlieren and shadowgraph imaging. There are some truly beautiful images that have been captured in those studies. A few of them are shown here. Our research goal is to supplement this existing data by using an optical data collection method. Our equipment and methodology are similar to previous optical studies with some important differences. Our technique is less intrusive in the hopes of better representing aerosols, which cannot be ignored or excluded as carriers of contagions. We also hope to minimize the variability that is seen in other studies by taking into account the type of vocal activity and other factors like volume and pitch that may affect the numbers that we see. The technique we are using in the lab is known as laser sheet imaging. The laser in the lab is a ND-YAG 532 nanometer pulsed laser. And 532 nanometers is in the green spectrum of visible light. As you can see here, the beam passes through a spreader, which transforms its shape into a flat sheet, which is about 2 or 3 millimeters in thickness. Particulate matter that enters this beam of light scatters that light into the lens of the camera here, and we get images of very small particulate matter that way. The participant will be seated on the opposite side of this barrier, and their mouth will be positioned at the small opening here. The barrier can be adjusted so that the participant will be positioned at 3 different distances from the laser sheet. All safety requirements will be met and exceeded when working with a high-power laser. Optical exposure is the primary concern, so all participants and researchers will wear safety goggles specifically manufactured for protection from a laser of this wavelength and power. Curtains that are not shown in the model will also block line of sight to most of the laser sheet as an additional precaution. And the risk of harm due to physical exposure to the beam is very small, but regardless, physical access will be blocked as much as possible, and a gown and some additional covering will also be available. No participants have been brought in yet at the time of this recording, but we are very close to that point. So for data collection, black and white images are captured rapidly by the camera. Since the images are not in color, the setup must be calibrated for high contrast images, such that any particles that pass through the plane of illumination stand out in stark contrast to the background. We can string these images together to display them as a video also. The image contrast allows for simple analysis using an image processing program such as ND-YAG, a free program developed by the National Institutes of Health. The open source nature of the program is conducive to running specific analysis on large batches of images all at once, and it can give us a particle count for each image in a sequence. A graph of this data shows how particle count in the plane of illumination changes over time. As a test, a researcher performed a vocal exercise called a lip trill that is expected to cause a continuous airflow and a large number of expelled particles. That's basically a fancy way of saying he made a sound. As expected, the start and end times of the exercise are obvious, but a background level of airborne particles exists even when no vocal activity is happening, and this is due to pre-existing airborne dust and particles in the room. This video corresponds to the graph in the previous slide, and as you can see there, many more particles enter the plane of illumination when the vocal exercise is performed. However, the background particles do make it difficult to visually distinguish between dust in the room and orally emitted particles. The interference obscures the data we're trying to measure. I'll play back that video one more time. So work is currently being done to add an enclosure and an air filtration system to reduce the effect of these background particles. The enclosure must continue to be non-intrusive, so its effectiveness may prove to be limited. Regardless, we can also numerically estimate the interference and take that into account. Since only a 2-dimensional slice of the airflow can be illuminated, the barrier will be moved to 3 different distances from the plane of illumination, so the behavior and number of particles at different distances from the source, the person speaking or singing, can be investigated more thoroughly. So what do we hope to accomplish in the upcoming participant trials? Well, by having people perform pre-selected vocal activities and exercises, the data will shed some light on how strongly different factors affect the number and behavior of airborne particles. Early trials will investigate speech versus singing and breathing, and also the effects of volume and pitch. We can normalize these findings by looking at relative effects of each variable and hopefully draw some conclusions about general levels of aerosol exposure in relevant scenarios. And another ongoing project is the development of computational programs that model exhaled airflow. The data collected from this lab can provide guidance for the development of those models, as well as validation of predictions made by the models in order to test their accuracy. Once better developed and verified, those computational models can also be used to estimate exposure to aerosols under various conditions. Our hope is that these efforts will help to inform safety guidelines for face-to-face activities moving forward. If you have any questions about the presentation, please feel free to post them to the video and they will be answered shortly. Thank you.